Okay, so today let me recall just some definitions we did a couple of weeks back. So we had done this notion of linear parametric function. So you have a linear model y, x, beta, and sigma squared I. Sigma squared represents the variance of the errors, and covariance is 0 or uncorrelated variables. And we said that a linear parametric function that is P transpose beta, where P is a vector in Rm, is said to be estimable if you could find a vector L in Rn so that the mean of L transpose Y is P transpose beta, right? So in other words, L transpose Y was an unbiased estimate of P transpose beta. That was the meaning of a linear parametric estimate to be estimable. Right? So then we also showed this thing in February 9th that we said that the linear parametric function P transpose beta is estimable if and only if P belong to the column space of X transpose. That is if there's a Y, so that X transpose Y equal to Z. This proof we had done. And I'd like to start from here and then just do a quick revision and go on to what are called best linear unbiased estimators. That's the topic for this week, and the Gauss-Markov theorem that I would like to show you all. So first is I'd like to understand how many, see, for example, P transpose beta is an estimable, means P is in the columns of X transpose. So I'd like to see how many components of beta are estimable in a clear way. Suppose I have enough P transpose beta which are all linearly independent, then that will give me the number of components of beta that are estimable or not. So let me just write these thoughts down so that we can just show you. So let me start with independent. One second. So let me do this. Let me try to find how many independent parametric linear functions, how to sort of identify them so that you can get an idea of how many components of beta we can estimate. Okay, so again, I'll start with this theorem. So this theorem says that what? This theorem says that if P transpose beta is estimable, then P has to become P in the column space of X transpose, right? So first fact is from the above theorem, right? Above, and I think this was discussed on the Feb 9th week, way back in the third week or second week. So it's clear that the number of, so if you look at this theorem, look at the number of linearly independent estimable linear parametric functions is the same as the dimension of the column space X transpose. Okay, so it's clear that the number, so the crucial is independent, right? Independent. Maybe I should be clear, number of linear independent, what I wanted to say. Let me just write this down. Linear independent. Estimable independent, estimable linear parametric functions. So that's of the form P transpose beta, right? Functions is how many are there. That means there's so many independent ones. Means that each of them has to be on a column space A transpose. So for each linear independent vector on this side, you'll find a different linear independent on that side. So it's the same as the dimension of column space A transpose is equal to the dimension of the column space of X transpose. That's clear. That's very good. That's one thing we immediately have to sort of understand immediately, right? So now one can now try to understand this. So what is that's the same as that's the same as the rank of X. Right? That's how the fundamental subspecies of a matrix are related, right? Very good. So once we have this, then we know beta is a vector. What does this imply? Does it imply one crucial fact that beta is a vector in R, right? So now P transpose beta, if you have enough independent P transpose beta, you can estimate all components of beta estimable. That means, therefore, the simple exercise to think about, that all the components of beta are estimable if and only if the rank of X is n. So therefore, all components of beta are estimable if and only if the rank of X is full rank, that is, the rank of X is n. And that's what we call it. So, but then we also know other things in the algebra, right? So this implies some next fact of the following, that X is full rank, so full column rank, let's say. So X is full column rank. Right. That's if and only if what happens, if and only if X transpose X is non-singular. Right? It's easy to see, right? It's a simple exercise. X transpose X is non-singular. Right? That's just a fact in algebra. But that would imply what? That in this case, if X transpose X is non-singular, in this case, the normal equations, we've seen this before, the normal equations have a unique solution, right? So normally normal equations have a unique solution. Right. So what is the solution given by that is beta hat would indeed be X, it's invertible. I could just take it that side, X transpose inverse, X transpose Y. That would be this is the vector. This is how I would define my. So this is in fact the unique least square estimate, right? So in fact, it is the unique least square estimate. Let's say of beta. So this is something that one can easily observe. So suppose the rank of X is full M, then the normal equation of a unique solution given by X transpose X inverse X transpose Y, and then all components of beta are estimable in that sense. That's clear. That's one thing we established in this. Okay. So today we'll try to go and understand among all the linear unbiased estimators how to identify the best one. Okay, this is called the bluest. Blue definition is called blue. So I will need space. So today I'll go next page. So down, give me that definition. So this is the definition today is blue. Blue is BLUE. That is the best linear unbiased estimator. Or estimate, I should say, not estimate, estimate. I should say. So I want to give a specific, this is called blue. So I'll give us a definition to identify among all linear unbiased estimates, which is the best one. Okay. So I'll give a criteria and we'll work with the criteria. So we'll write down and let's say an or a linear estimate. So linear estimate means it's just a function of Y, right? So let's write down, so A transpose Y is called blue. So it's called the best linear unbiased estimator for estimating so let me write down estimating. Now I will just be a little bit careful. I'll say estimating an estimable linear parametric function okay, let's call it P transpose beta. P transpose beta. If two things happen. So first, I already said let's leave it as blue. The blue is the purple one, pink one. So blue means what? First thing you notice, it's an unbiased estimate, right? So if two things happen, one, if the mean of the estimator matches the two values, so the expected value of A transpose Y is same as, so A also is a vector, I guess, so we'll put a vector, is P transpose beta. That's the first thing. Then this is true for all beta and Rn. Then the second thing is the variance should be the smallest among all possible unbiased estimators. So variance of A transpose Y should be less than equal to variance of all linear, that is L transpose Y, right? For all L and Rn, sorry, such that L transpose Y is an unbiased estimator of P transpose beta. Beta of P transpose beta. Okay. So that's the first definition. So blue means among all possible estimators, it has least variance, and the estimator is also unbiased. This is the first thing, the definition of blue. So simple definition, you just minimize the variance, keeping the mean the same as the estimable quantity. So it's a very nice theorem, which we'll try and show today. Let's try. I'll show a theorem, and in the next class, I'll try and sort of show this whole thing. So the theorem, next video tape, let's say, recording. So this theorem is a very famous theorem. It's called the Gauss-Markov Theorem, sort of the fundamental theorem in this area. So what does the theorem say? So the theorem says the following. So suppose you have a linear model, you have an estimable linear parametric function, then it'll tell you that the least square estimate is the best linear unbiased estimate of the transmitter. That's what it'll tell. So let's start again. So let's try this, write this down. So suppose let's write the linear model in a short form notation. Suppose Y X beta and let's say uncorrelated and variance sigma squared error terms we have the linear model. So that's the basic model we start with, like before, right? And we'll also assume and let's say P transpose beta be an estimable linear parametric function. So let's say be an estimable linear parametric function. So then the theorem says the following. Then the least squared estimate, let's write this down, least square estimate, that is the one that minimizes the square distance from the true estimate, least square estimate of P transpose beta So let me call it as, let's say written as P transpose R beta hat, that we always call. So and now I'll assume it is for some solution, right? So for some solution, of the normal equation. So let's say normal equations are some sort of normal equations. So let's call it as, let's say, X transpose X beta hat is equal to X transpose Y. The equation I'm solving. So the least square solution is in fact the blue of P transpose. In fact, the blue. So it's the best linear unbiased estimate of P transpose beta. That means you can't do better. So what's the blue? A blue is one. A blue is one that minimizes all the linear minimizes variance. All linear unbiased estimators. And now what the theorem was telling you is that to find the blue, all you have to do is find the least square estimate, as long as P times beta is estimable. So this is the first thing we will prove in this week, and then we'll do some consequences of this.